Welcome everyone to this detailed technical review. And I should probably explicitly state right up front, just for full transparency, that this is actually an AI-generated analysis.
Right. But we're still here to unpack the concepts just like normal.
Exactly. And today we are cracking open a really fascinating book. It's called Becoming a Data Head: How to Think, Speak, and Understand Data Science, Statistics, and Machine Learning.
Which is such a critical topic right now. Our mission for this review is basically to help you build a mental model for understanding data. Because, despite all the massive hype around the data field, something like 87% of data science projects just completely fail.
Wait, 87%? That's a staggering number.
Yeah, it's huge. They just never make it into production. And what's really interesting is that this failure is almost never due to a lack of computing power. It's not because the algorithms aren't sophisticated enough.
Right, so it's not actually a math problem at all.
No, it's a communication problem. There's this massive gulf between the data workers who actually build the models and the executives who, request them. They frequently fail to align on the core business problem before anyone even writes a single line of code.
So today, we're acting as your expert guides to help you bridge that gap. We want to give you the vocabulary to actually interrogate your data, rather than just blindly trusting whatever's on a dashboard.
Exactly. And to do that, before we can even talk about analyzing data, we have to make sure we're solving the right problem, which brings up a foundational question. How do we even differentiate between abstract knowledge and actual data?
Okay, let's unpack this,
Yeah.
because the book provides a really precise definition. Data is specifically encoded information. Abstract knowledge only becomes data when it's captured in a format a machine can analyze.
Right. Like, think about your own company. You might have a ton of abstract knowledge about your monthly marketing campaigns. You ran some TV ads, you did some social media stuff.
But it's not data yet.
Exactly. That knowledge only becomes data when it's encoded into a structured table, tracking the exact financial spend and the generated revenue for each specific campaign.
And once that information is encoded, the next step before any analysis is categorizing what kind of data you have.
Hmm.
The book draws a really hard line between observational data and experimental data.
Yeah, so observational data is information that's just passively collected. Think of like website clicks or grocery store transaction records. It's just sitting in a database waiting for someone to look at it.
Which sounds great, right? Because it's cheap and it's everywhere. But it's incredibly vulnerable to hidden, confounding features. You're observing what happened, but you don't know why it happened.
Precisely. Which brings us to experimental data, which is kind of the gold standard for statisticians. This is actively collected through deliberate methodology.
Like randomly assigning treatments and controls, right?
Yes, that random assignment is the magic ingredient. It naturally balances out all those confounding variables. Clinical drug trials are the classic example, but in business, this is your digital marketing A/B testing.
Okay, so establishing the data type is step one. But the book also talks about thinking statistically, which basically means viewing your data through a lens of variation.
I love this concept. We constantly forget that data rarely gives you an absolute unchanging fact. Every metric has inherent variance.
Right, fluctuations are totally normal. If your weekly customer satisfaction score drops 2 points, executives usually panic. They think customer service just fell off a cliff.
But a statistical mindset tells you that might just be the natural variation of sampling different people on different days. If you don't view data through that lens, you're going to constantly overreact to random noise.
So we've collected the data, we categorized it, we understand variance. Now we have to vigorously interrogate it, because if you don't scrutinize the raw material, you just get garbage in, garbage out.
And the book illustrates this with a really terrifying historical example, the Space Shuttle Challenger disaster.
Yeah, that part is heavy. It's a profound example of what happens when you don't ask the right questions about your data. In 1986, engineers were evaluating the O-rings on the solid rocket boosters.
Right, and they had beta showing past incidents of thermal distress on those O-rings. But the problem is, they only looked at a partial data set.
They only looked at the flights where damage actually occurred. They completely left out the successful trial flights.
It's a tragic oversight, because if they had just plotted the missing data, the perfect flights where nothing went wrong, they would have seen a glaring pattern.
The successful flights happened at warmer temperatures.
Exactly. If analysts had included that missing data and just run a standard binomial regression model, it would have shown a severe trend predicting failure at lower temperatures.
And on the morning of the Challenger launch, the forecast was an unprecedented 31 degrees Fahrenheit.
Right. That model would have predicted that 5 out of the 6 primary O-rings were highly likely to fail.
It's just wild. It shows the catastrophic consequences of not asking, hey, what data is missing here? But, even when you have all the data perfectly laid out, human intuition can still misinterpret it,
Sure.
especially with probabilities.
Oh, absolutely. Which brings us to the laptop virus scenario the book mentions. This is an exploration of Bayesian probability, which is how initial probabilities change when you introduce new evidence.
We should actually run the numbers on this one because it really exposes a massive blind spot we all have.
Let's do it. So imagine an organization with 10,000 laptops. And suppose 1% of those laptops are infected with a deadly virus.
Okay, so 1% of 10,000. That means 100 laptops actually have the virus and 9,900 are completely clean.
Now, the IT department uses a diagnostic test that is 99% accurate, and here is where human intuition totally fails.
Right, because if that test is 99% accurate and your specific laptop tests positive,
Yeah.
you naturally assume there's a 99% chance you have the virus.
But you have to look at the volume of false positives. Let's trace the math. We test all 10,000 laptops. For the 100 that are actually infected, the test catches 99 of them. Those are our true positives.
Okay, got it. 99 true positives.
But then we apply that exact same test to the 9,900 healthy laptops. And since the test has a 1% error rate, it's going to incorrectly flag 1% of those clean machines.
Oh, wow. 1% of 9,900 is 99.
Yes, those are our false positives.
That is crazy. So if my laptop gets a positive result, it goes into a bucket that has 99 true positives and 99 false positives.
Exactly. The bucket is perfectly split down the middle. Therefore, a positive result from a 99% accurate test still only means there is a 50% probability your laptop actually has the virus.
It's basically a coin toss. Understanding that conditional probability is just so crucial. It stops organizations from panicking over diagnostic tests.
Or from misinterpreting sweeping statistical claims in general.
Okay, so with a firm grasp on questioning raw data and probabilities, let's transition into the actual toolbox, the specific machine learning algorithms. Let's start with unsupervised learning, specifically principal component analysis, or PCA.
So unsupervised learning is fascinating because these algorithms operate on datasets that don't have predefined labels. You aren't telling the computer what to look for. It's just searching for hidden structures within the raw numbers.
And PCA is specifically used for dimensionality reduction, right?
Yes. The book uses a really helpful vehicle analogy for this. Imagine you have a dataset of hundreds of cars, and for every single car, you have 30 separate variables.
Like columns for miles per gallon, weight, horsepower, tire size, 30 dimensions of data, which is just impossible for a human to visualize.
Exactly. So PCA resolves this by squishing the dataset down. The algorithm evaluates all 30 variables, finds mathematical correlations, and calculates weights to combine them into entirely new composite features.
Which are the principal components. So instead of looking at 30 graphs, the algorithm sees that miles per gallon, weight, and horsepower always interact. And it just bundles them together into a single component you could call efficiency.
Precisely. And by doing this, the math allows you to keep something like 91% of the original information while using only 4 of these composite features. You can just ignore the other 26 columns.
That dramatically simplifies things. But most businesses don't just want to explore data, they want prediction. They want to know what happens next, which shifts us to supervised learning.
Right. Supervised learning uses datasets that already contain predefined labels. You're actively training the algorithm to predict those labels for future data. The most common application is classification models.
Like logistic regression or decision trees. You're asking the model to put data into discrete categories, like approved or denied for a loan.
Or spam versus not spam. But assessing how well these classification models actually work introduces a major trap. The book details the mechanics of the confusion matrix, which cross-references what the model predicted against the actual truth.
It breaks it into true positives, true negatives, false positives, and false negatives. Right?
Exactly. And the metric you need to pay closest attention to is the true positive rate, sometimes called sensitivity or recall. It measures the proportion of actual positive cases the model correctly identified.
And you have to separate that from the false positive rate. Because misunderstanding these metrics is a huge pitfall. A lot of business leaders evaluate models based just on a generalized accuracy percentage.
Which is incredibly dangerous.
It really is. Like, let's say a bank processes 10,000 transactions. and only 10 are fraudulent. If I build a lazy algorithm that just says not fraudulent every single time, I will be right 9,990 times.
So your model has an accuracy rate of 99.9%.
Exactly. Which sounds amazing in a pitch meeting. But the model is entirely useless because it missed every single instance of fraud. Its sensitivity is 0.
The confusion matrix forces you to look past those superficial metrics and see how the model is failing. Now, everything we've discussed so far handles structured tables of numbers, but we have to acknowledge that the vast majority of modern data doesn't live in a neat spreadsheet.
Right? It's unstructured. It's massive repositories of emails, social media posts, images, and analyzing that requires fundamentally different architectures. Let's talk about text analytics, because computers do not actually read text.
No, they don't have any human understanding of narrative or sarcasm.
Yeah.
So to process qualitative words, the algorithm literally converts letters into mathematical structures using the bag of words model.
And this is where a sentence is completely stripped of its grammatical order, right?
Yes. The computer treats the sentence like Scrabble tiles thrown into a bag. It's just a random collection of individual tokens.
Wait, so the computer just rips up the sentence, ignores all the grammar, and turns it into a giant spreadsheet of word tallies.
That is exactly right. To create a document term matrix, the algorithm builds a massive dictionary of every unique word across all documents. Each word becomes a column, each document becomes a row, and it just populates the table with raw frequency counts.
Like putting a number in the matrix to say the word terrible appeared 3 times.
Right. So if I write the dog bit the man or the man bit the dog to a bag of words model, those sentences are mathematically identical.
Because grammatical syntax is totally destroyed. That really puts the limitations of things like automated sentiment analysis into perspective.
It does. But the demand to process incredibly vast, unstructured data has driven the industry toward deep learning, which relies on artificial neural networks.
And these are structurally inspired by the human brain, but they operate through massive, strict math. The architecture is just fascinating.
Yeah, an artificial neural network consists of interconnected nodes, or neurons, arranged in multiple layers. Every neuron contains an equation called an activation function. You feed data into the input layer, and the results are passed forward to subsequent hidden layers.
And these layers of equations stack together to form remarkably complex predictive models. Deep learning can find incredibly obscure patterns that traditional models just can't see.
But that complexity introduces a massive technical risk. Because an artificial neural network can contain millions of interacting parameters across dozens of layers, they often become completely unexplainable black boxes.
Right. Even the engineers who built the network can't always retrace the mathematical steps it took to arrive at a specific output.
You know what went in and what came out, but the middle is a billion equations firing at once. And deploying these black boxes for sensitive, real-world human issues requires intense scrutiny.
The book brings up applications like predicting criminal recidivism, or screening resumes, or facial scanning. If the historical data used to train the network contains flawed human decisions, the algorithm doesn't know any better.
Exactly. It will just mathematically encode and automate those historical flaws at a massive, rapid scale. You cannot blindly accept the output just because the math is complex. The responsibility remains entirely on the human operators.
Which is the perfect transition to the final section of our review. The most sophisticated neural network will absolutely fail if the humans deploying it can't communicate.
Right. Technical proficiency means nothing if you have human bottlenecks. The book categorizes 3 distinct data personalities you'll encounter in any corporate environment. The first is the data enthusiast.
Ah, the enthusiast. They're highly optimistic, they blindly trust algorithms, and they view data science as this magic wand that will fix next quarter's revenue.
And they frequently overpromise results, which sets everyone up for failure. Then, usually sitting right across from them, is the data cynic.
Cynics just rely solely on their gut instinct, right?
Yeah, they reject data-driven initiatives out of hand. If you present them with statistical results they don't like, they will deliberately nitpick tiny details just to dismiss the entire analysis.
They use skepticism as a weapon. But the ideal standard, according to the book, is the third personality, the data head.
Right. Data heads balance technical knowledge with deep domain expertise. And most importantly, they maintain a healthy, empathetic skepticism.
They're the ones asking, what data is missing? Or did we account for false positives? Organizations succeed when they cultivate data heads who can translate statistical limitations into actual business requirements.
It's really the only way to survive in this landscape, and that leaves you with a final, really important reflection to mull over. The data we collect is always merely a proxy for reality. It's just an encoded approximation.
Right. And at the exact same time, our deep learning models are becoming increasingly complex and completely opaque.
So if data is only ever a proxy, and our most powerful algorithms are unexplainable black boxes, how do organizations ensure that these mathematical proxies don't permanently replace human judgment and ethical responsibility?
That is a perfect thought to end on. We strongly recommend that you read the actual book, Becoming a Data Head, to fully grasp the detailed math and the complex scenarios we've been exploring today.
It's an essential read.
To all the friends of the show listening, please subscribe to this broadcast for future comprehensive analyses into the data landscape. We wish you a great day.